Hi, everyone. My name is Joseph Lattanzi, and my presentation asks, who comes back? Can we predict which ICU patients will be readmitted within 30 days using machine learning? Over the next 40 minutes, I'll show you a complete data science pipeline from over 545,000 patients to actionable clinical insights. $26 billion in annual cost. Uh, 1 in 5 Medicare patients readmitted within 30 days. The Centers for Medicare and Medicaid tracks this and penalize hospitals with high rates. Beyond money, this means patients can suffer, they have more procedures, they have complications, they have higher mortality risks. ICU patients face even higher risks than just regular hospital readmissions. So the question is, can we identify high-risk patients before a discharge? My approach has 4 stages. First is the data, which is Mimic IV. That's the name of the data. It has 545,316 IECU readmissions or admissions, excuse me, from 2008 to 2019 with 6 interconnected tables. Uh, Next is features. I engineered 57 features capturing comorbidity burden, medication complexity, and healthcare utilization. Next is models, which has 3 complementary approaches: logistic regression for interpretability, random forest for nonlinear patterns, and finally XGBoost for performance. Lastly is impact. I translated this into risk stratification, an ROI analysis, and resource optimization. Models only matter if they can be deployed, right? Overall, this is a supervised learning problem. We know the outcome of these patients. Every patient in our data set has a label, whether they've been readmitted or not readmitted within 30 days. The model learns patterns from over 367,000 labeled training examples to predict future unlabeled patients. But so this differs from an unsupervised learning like clustering, where we discover patterns without knowing the outcomes. The Mimic IV dataset. This is from Beth Israel Deaconess from 2008 to 2019. It has 380,000 patients, 500,000 admissions, 120 million lab measurements, 26 million prescriptions. It is a rich, dense, giant data set, which I was lucky enough to get my hands on. It's comprehensive. It gives you the entire clinical picture of a patient. It's granular. It has time-stamped events, not summaries. At some points, too granular to even analyze, right? Uh, and it's validated. It's peer-reviewed. It's widely used. I had to take a class and get recommendations to use it. And it's realistic. It's real-world data. With all of its messiness, if it works here, it can work in practice. And here is the structure of the data. It's 6 interconnected tables. Admissions is my anchor. It has 500,000 encounters. Patients has demographics, uh, then clinical detail, 4.8 million diagnoses, 26 million prescriptions, 650,000 procedures, and over 120 million lab measurements. So as you can see, it kind of moves down the line there from the admissions to the patient and then what that patient has under it. And so the challenge is, how do I turn 120 million lab rows into patient level features? My solution is to aggregate complexity metrics. So instead of raw lab values, I'll compute total tests ordered and test diversity proxies for monitoring intensity. The absence of tests is informative too. You know, if patients weren't given a test rather than given a test, can that be used? You know, were there no cardiac enzymes drawn? Then it's not a cardiac case. So looking at missing data sometimes is informative, could prove to be useful. The data integration pipeline. So from 6 tables to one data set. link everything via patient and admission IDs. Those were the two linking factors there. Uh, filtering to avoid or filter to valid discharges. So removed stays under a day or over a year. So things that probably slip through the cracks. There were not many of them. So calculating 30-day readmission by comparing discharge time to next admission. So getting our actual readmission rate, which, we know that the average is 20%, but we'll find out what this data set actually held, right? Um, and then aggregate millions of events into patient level features. So medication count, therapeutic diversity, high-risk drug flags, same for labs and procedures and diagnoses. And the result of that is 545,316 eligible admissions, with 57 features each, ready for machine learning. The baseline. So this is what I was alluding to. The 30-day readmission rate is 20.03% were readmitted within 30 days. So out of 545,000 discharges, that's 109,000 readmissions. I feel like when you think about it in those large of numbers, it shows you how big of a problem this really is. That's higher than the national average, which is 14.67%. Mind you, that is regular hospital readmissions. These are ICU readmissions. It matches Medicare's 20% of ICU readmissions. And it makes sense. ICU patients are the sickest. So this 20% baseline is going to be critical for this modeling. A model predicting no readmission for everyone would be 80% accurate, but useless, right? Uh, a challenge is identifying which 20% will return. Uh, and that's the class imbalance problem we'll address throughout this process. So who are these patients? Readmitted patients, as you might imagine, are older, a median of 67 in age versus 64 for non-readmitted. They have longer ICU stays, which would also make sense. A sicker patient probably stays longer, the median stay being 6.8 days versus 5.9 days. Um, and emergency admissions have higher risk than elective procedures. So they're not surprising findings, but they validate the data behaves as expected clinically. The question is whether comprehensive feature engineering can capture more nuanced patterns than these ones that you see here that we could probably expect. So some clinical complexity patterns. Readmitted patients are more complex across every dimension. So 20% more diagnoses. As you can see here, that's the median of 12 versus 10. 32% more medications, 29 versus 22, indicating that severe polypharmacy can increase readmission rate. Most striking, 48% more lab tests, 80 versus 54, reflecting greater diagnostic uncertainty and monitoring intensity. So the more labs that they're given, you can assume the more worried doctors are, the less sure they are with what they have. So the more lab tests, there's a much higher likelihood that they return to the ICU. Procedures are similar, suggesting that complexity isn't driven by surgical interventions, but more so by medical complexity. And you can see that in the bottom right hand corner here. They look pretty similar. And the systematic pattern across all measures validates the feature engineering approach that I'll be taking. Data quality and completeness. So this is messy real world data. I wouldn't say it is as messy as a lot of other data sets. It's pretty well put together. And so here on the right, you can see a chart of the data completeness by feature category. So demographics is 99% complete, which is excellent. Labs are 96% complete. Medications are 92% complete, which is solid. Uh, Diagnoses are 85% and procedures are 73. It's acceptable but imperfect. And the key insight here that I alluded to earlier is that missingness can be informative. So no cardiac biomarkers, there's not a cardiac case. Uh, Only a few procedures, then a medical admission, maybe not surgery, right? Um, so we made strategic exclusions for 19,442 patients with data quality issues in the race field. And we assumed those were collection failures. It was just an unknown declined race. Um, 531 with no diagnoses that were likely errors. But we kept patients with missing procedures or labs because absence can carry clinical meaning, as I said. And if this model works with messy real world data, it can work in practice. So I thought uh, if we can keep it as messy as it still makes sense and use it, then it will be informative past just this data set. The feature engineering overview. So from 150 million raw records to 57 predictive features across four categories. Comorbidity indices like Charlson score. Charlson score is a well-known uh, comorbidity index in the healthcare world. It combines a lot of things, and we recreated it for these purposes as well. Uh, our mean, they captured disease burden. Uh, our mean is zero point zero 0.07, flagging heart failure, diabetes, pulmonary disease. Healthcare utilization measures medication count, average 26 prescriptions, lab diversity, procedure complexity. Medication risk, that can include polypharmacy flags, which we'll see to be useful later on, uh, in a mean of 9.3 on a scale of 3 to 58. Uh, in like a clinical complexity score, multi-system involvement, it had a mean of 9.3. These aren't raw clinical values, they're de-engineered metrics capturing patient complexity in ways that predict readmission. But the bottom line is we had 57 features, zero missing values, and they're all clinically validated. And here is the feature engineering in action. So some examples, 26 million prescription records become medication count per patient. 28 medications flag severe polypharmacy. ICD code I50.9 becomes has heart failure equals true, a condition with a 34% readmission rate. 120 million lab results become lab diversity score of 8 categories, testing the breadth, signals, diagnostic uncertainty. We create interaction features. Age 72 plus 15 medications equals elderly polypharmacy flag. Um, Clinical complexity score combines multiple dimensions. This patient scores 14 out of 58, capturing moderate high complexity. Um, we're not using raw lab values or vital signs. We're capturing the clinical complexity patterns. And these are just a few examples of the many things that I did while creating these features. And there was a lot of trial and error, as you can imagine, with things like the um, combinations and things of that sort. But we found 57. And here is the data split strategy. This is an important part, I think. So it's a temporal split, not random sampling, which is something that I wasn't used to. 70% of it is training data, so 381,728 patients from 2008 to 2017. 15% validation, so 81,794 patients from 2017 to 2018 for threshold tuning. and then 15% tests. So 81,794 patients from 2018 to 2019, which are completely held out. So though the splits make sense, why am I using temporal? So four reasons. It stimulates deployment or simulates deployment. So models train on historical data, predicting future patients. It prevents data leakage. So healthcare has temporal patterns like treatment protocol changes. So it accounts for those. It provides conservative estimates. It tests whether patterns remain stable, and it's clinically realistic. And this was the one that clicked for me. Deployed models, what must work on patients that they've never seen. Readmission rates keep stable across all splits. 20% confirms that the outcome prevalence is consistent. But when you think about it in the sense that, we want to keep testing this model on patients as they're coming in because time matters. So, um, we want to test it on 2008 to 2017, and we want it to then move on and see how it does there. And as it gets closer and closer to real time, then we're working in the right direction. So the modeling approach, we'll spend some time here. There are three complementary models I mentioned already. Logistic regression, which is an interpretable baseline. It's the clinical standard. It gives coefficients physicians they can gives coefficients to physicians that they can understand. Um, Random forest captures nonlinear relationships, handles feature interactions automatically. XGBoost last is the state-of-the-art gradient boosting, which has the best performance. Didn't use any deep learning. There were insufficient temporal sequences. Didn't choose to use SVM methods. It was too computationally expensive. As you can imagine, when I'm dealing with over 120 million rows of things, we have to be cognizant of cost of some of these functions. And we didn't use naive Bayes. The features are a lot of the times correlated here. So that wasn't an option. Our ensemble approach balances interpretability with performance, as you'll see, and you're going to need both for clinical deployment, right? So we'll take a look at logistic regression, random forest, and XGBoost here. Um, how logistic regression works, it calculates a weighted sum of the features. So it's very simple. If I wanted to take age times zero point zero 0.02 plus medication count times 0.15 plus the length of stay times zero point zero 0.08, and then convert that to a probability using a logistic function. It's simple, it's transparent, but it assumes those linear relationships, right? So length of stay times a factor. So it assumes linear relationships. Random forest is a little bit different. Random forest, builds 500 decision trees. Each tree will ask yes or no questions. For example, is medication count greater than 25? Yes. Then is age greater than 70? No. And then it'll predict. Um, it could predict low risk after that. So the 500 trees then vote, and the majority wins. So it handles nonlinear patterns, but it's also harder to interpret because of all those decisions and voting that goes on throughout that time. And lastly, XGBoost. XGBoost is complicated. It builds trees sequentially. So the first tree predicts and identifies any errors. The second tree then focuses on those errors, and the third tree fixes the remaining errors. So, for example, as you'll see later, after 407 iterations of, that's when my tree stopping stop, you combine all of those trees, and it has the best performance, but it is opaque. There's thousands of rules. There's 407 trees. It's impossible to explain, but it has really good predictive power. So that's how all of these work. That's why we're using them. That's why we're not using some of the other methods. I thought it was important to understand why I took this modeling approach. So for training methodology, um, There are a few things in here that are new. So, fivefold cross-validation for hyperparameters. Uh, and critical decision would be threshold optimization, right? A default of 0.05 is a threshold, which you use for a lot of decision making, fails when you have a 20% class imbalance, as we do here. Um, so a model would rarely predict readmission. And on my first pass through, it didn't predict any when I had it set at zero point 0.5. So we had to work on some threshold optimization. I used something called Uden's index. It's doesn't default at zero point 0.5 and found that the optimal threshold of 0.197 for XGBoost, which is way lower than zero point 0.5, as you can imagine. And as you also may notice, it hangs right around that 20%. Uh, Early stopping. So that's something that I just kind of touched on, but it prevents overfitting. So it doesn't keep on fitting trees. It's smart enough to use early stopping to stop at its own iteration where it finds that threshold optimal instead of going until you tell the max, right? Um, and then for regularization, for logistic regression, used a L2 penalty. And for XGBoost, we set some learning rates and max depth and subsampling. Um, but most importantly, what we're going to be looking at mainly, and we'll look at some other things too, is going to be the area under the curve, the AUC. AUC handles class imbalance better than accuracy, I believe. So that is going to be our primary way to tell how successful these models are at predicting readmission within 30 days. So moving on. So we trained all of those models on the 70% of our test data, or training data, excuse me. And we're now looking at the validation set performance. So with 81,794 patients, logistic regression had an AUC of 6.55. You can see AUC here, um, which is a solid baseline. We moved up a bit with random forest at 6.660, which is only a 5 point improvement. And then XGBoost came along and we were at 0.695. It was the clear winner, um, and all significantly are significantly better than zero point 0.5. Now we'll get into some of the uh, problems with having things, even though it's better than zero point 0.5, it's not perfect. So that can cause some problems in real world translation later on. We'll get into that. But, sitting right around 70% for XGBoost is pretty impressive with the class imbalance that we had. XGBoost also achieves 68% sensitivity. Uh, it catches 2 out of 3 readmissions, basically. 60% specificity, a PPV of 30.41. So to explain that, among the flagged patients, 30% will actually readmit versus the 20% baseline. So we gain basically a 52% relative improvement on what we had before. So small performance differences suggest linear relationships dominate within this. XGBoost was selected for the final test evaluation. As you can see, this whole row here was performing better, and we want the highest performance. The minimal gap between validation and test AUC indicates good generalization. So, uh, hopeful that the model didn't overfit. And over here, you can see the ROC curve comparison for the sets. It can be kind of hard to see, but logistic regression and random forest are green and blue, and they basically overlap the whole way here. And you can see XGBoost really show itself and come over the top here over those two methods. Moving on. Oh, the laser pointer. Final model performance. So this is where the rubber hits the road. The final test set performance on, again, 81,794 completely held out patients from 2018 to 2019. The test AUC was 0.683, which you can see here. Uh, Only a 1.28% drop from validation, and you can see all the changes in this column right here, which really I was excited about. It means that the model had exceptional generalization. You could see that these are really minimal changes here. Uh, so it didn't overfit. It generalized great. We're testing it on brand new, unseen patients. And the sensitivity actually increased to 68.8%, which means it's identifying every 7 out of 10 readmissions. To touch quickly on these bottom two, PPV and MPV, I had to spend some time learning about these, but basically PPV, and it's you can kind of see it over here as well, is the positive predictive value. So it's the probability that a person with a positive test actually has the disease, and this disease meaning readmit, while the NPV or the negative predictive value is the probability that a person with a negative um, test result does not also, right? So it's like it's here and here, um, where they weren't readmitted. So as you can see, these aren't perfect. It's a false alarm. We have 34% false alarm. So we're flagging people that aren't going to get readmitted. Um, and as you can see, we have a 13.9% true positive and a 45% true negative. And false negative of missed is 6.3%. So as you can see, we're really leaning on the side of false positive being at 34%. Um, but only missing 6.3% is relatively good based on this class imbalance in my opinion. Um, so to touch on what PPV and MPV are here, so 29.8% PPV, that's a 49% improvement over the 20% baseline that we had. An NPV of 87.3. So when the model says low risk, it's correct 80% of the time. This minimal degradation proves that it has excellent generalization. Performance is um, really good and clinically meaningful, which is the most important. The confusion matrix shows those 11,000 true positives, which is something to be proud of, right? Something that you caught. So next, we will look at the actual predictive features in XGBoost. So what's actually driving this model and what predicts readmission? Medication count is the dominant predictor. Polypharmacy itself is a risk, not just what it treats. Then we have age. We have a hospital mortality flag third. So patients who almost died remain unstable. Length of stay, so longer ICU stays indicate higher acuity. Total clinical events is fifth. Diagnosis count is sixth. And then we move down into some of the lower ones there. Um, Unique lab types being ninth, so testing diversity signals, diagnostic causes diagnostic uncertainty. So all top features fall into two clusters, one being the core demographic acuity measures, that's in teal, and utilization complexity measures in red. Um, and the key finding is that all of these features are clinically sensible. There's no real algorithmic noise. You can go down the list of this and probably understand, even being someone like me that doesn't have very much clinical background. You can go down this and understand, like, hey, this makes sense. Like, someone who stays in the ICU longer is probably more likely to be readmitted. Somebody who has more tests done, somebody who has more diagnoses, and uh, someone who's older. It's just that these things make sense, which is always nice to check back in with reality. So financial impact, get into some ROI here because you need money to tie in. So some pretty great findings when it came to the ROI. So the financial impact across all hospital sizes. So we have a small community hospital, we have a medium regional hospital, and we have a large academic hospital. Uh, Now, these are estimates based on research that I did. So a small community hospital with 5,000 annual discharges, that would prevent 150 readmissions. And based on, the average readmission cost, as you can see here, being 26,000, that would be 2.75 million year over year, achieving 239% ROI. And you can see the ROI numbers down here. Um, as we move up, the medium regional has 450 readmissions prevented. You can see the gross savings, the net benefit, uh, and as you can see, the ROI just continues to go up as we get more annual discharges. And there's another small uh, graphic here with the net benefit. Now there is intervention costs to stand up a model and um, you know, keep it running, right? So I tried to factor that in, not just as gross savings. I wanted to try to get a net benefit of what that would be with the investment that you have to put into something like this, but also the payment that you get out. And some more clinical efficiency analysis here. So clinical efficiency is normally measured in numbers needed to screen. And as you can, like, you'll be able to see that this is often used for diseases as well, but this can be tied back to trying to see if someone will be readmitted. So, how many patients must we evaluate to prevent one adverse outcome? Uh, uh, my model achieves 13.4 in NNS, meaning we need to screen approximately 13 patients to prevent one readmission. It's remarkably efficient compared to other preventative interventions. Um, Now, again, I told you something like cancer screening, you usually have a 300 to 500 NNS. Uh, Understanding that this is very different, but just giving you something to compare it to. Uh, the number needed to treat, which you can see here, is even better at just 4 patients. So, meaning once we identify high-risk patients, treating just 4 prevents one readmission. So, that's really powerful stuff. And as you can see here, the model is 1.5 times more efficient than random selection, demonstrating clear clinical value. Clinical translation, matching resources to risk. So risk stratification enables tiered interventions. So the top third has a 33.1% readmission rate, the middle third having a 20% readmission rate, and the bottom third 10%, which is 40% lower. Um, So the clinical insight is that high-risk groups in the red here contain 52.5% of all readmissions, despite only being 33% of patients. As you can tell, these are the percent of the cohort here is 33% for each, but it has 52%, over 52% of the readmissions um, in the numbers here. So once you match intensity to risk, intensive transitional care for high risk home visits, 48-hour follow-ups, it's $800 to $1,000 a patient. Um, when you get into standard follow-up, it's $400 to $600 a patient with phone calls and making appointments. And in the low risk tier, you have, minimal TCM, and TCM is transitional care management, um, and some education materials. So looking at the calibration of the models, and I did go back to all 3 models that were evaluated here. Um, we're checking are the probabilities accurate? So we use something called a Breyer score. And the Breyer score having, our Breyer score was 0.146, um, which is good. Good is usually under 0.25, so well under that, which is good. When we go to the expected calibration error, that is 0.003, and it's considered excellent if it's less than 0.05. And so what does that mean? So when the model predicts 30% risk, approximately 30% actually readmit. So probabilities are trustworthy across all levels, and that matters for deployment. Clinicians can use scores for shared decision making. Your readmission risk is 35% higher than your average. Resource allocation can be based on absolute risk. So a clinician could say we'll provide intensive follow-up for anybody above 30%. Um, Not just rank ordering patients, giving an accurate probability estimates that they can act on. So perfect calibration would be points falling, all along these diagonal lines. And so as you can tell, um, this goes all the way up to one. So this shows the whole distance. This logistic regression starts to fall off around point 0.6, 0.75. Random forest stays along it, but deviates a bit. And as you can see, XGBoost stays pretty true to it. Up to that 0.75, it starts to deviate. You can see some of the noise coming off of these things as well. Um, but it does pretty well. Looking at the scores here, you can see that it does very well. So now for an uncomfortable truth. Model performance varies by race. So this was something I knew I needed to check on by the end of this, but the calibration graph shows different lines for different groups. As you can see here, they're labeled. And these are only um, the groups with enough patients to really run this. Uh, so they all should track diagonally for equity, right? So sensitivity ranges from 75.5% for Black or African American patients down to 64.3% for the white other European. That is an 11.2% difference or point disparity. Um, if we went outside and included the heterogeneous other category, it would have been 23 points. And so healthcare machine learning typically considers um, disparities above 10 points unacceptable, and that's, right where I am. So this is something that will need to be addressed in the future. Um, Looking at some possible causes, just looking at the data, uh, Black patients have 22% baseline readmission versus 20% for white patients. So a little bit higher risk may help that sensitivity. There's a sample imbalance. So if there's 50,000 white versus 11,000 Black patients, mean that the model could optimize for the majority. So a single threshold may not be the answer for all groups. So um, I wouldn't deploy this with a single threshold. Test group specific thresholds require, monthly fairness monitoring and investigate those root causes further. So go, no go would be if prospective validation shows persistent 10-point disparities, then it would be a no go. And then quarterly audits would happen post deployment if it was below that. So it's a real limitation. A Black patient flagged 75% of the time versus a white other European patient being flagged 64% of the time is clinically meaningful, and potentially inequitable. So being transparent here, this would need a resolution before deployment. Study limitations. So single center data set. So we're just looking at Beth Israel Deaconess. For the Boston Hospital, its generalizability is uncertain. External validation typically shows a 5 to 15% AUC drop. And another one here is that it's pre-COVID data through 2019. It doesn't reflect telehealth or current patterns. And most critical, it's missing the post-discharge variables. There's no social determinants, so housing, transportation, food security, no medication adherence, no follow-up attendance, no caregiver support. Um, these directly drive readmissions, but aren't in our admission data. They're just data that wasn't there. And it's, as you can imagine, that data is much, much harder to get because it's harder to control. That creates a performance ceiling of around zero point 0.7 AUC, which is kind of what I had hit. And with a class imbalance, even the best model misses 1 in 3 readmissions. So some readmissions fundamentally are unpredictable from discharge data alone. So practical deployment challenges. Uh, Performance ceiling is 31% variance unexplained. So some readmissions fundamentally are unpredictable, as I had just said. Uh, there's a false positive burden. 70% of flagged patients don't readmit, which creates a resource waste. How much are you putting into those flagged patients? Another one is that XGBoost is, it is kind of a black box. So it could face physician resistance. I think if this went to deployment, it would have to really test whether the physician wants to know exactly what's going on within that, or are those features enough to have them be like, oh, okay, we need to look at this and that. Or do you want to bounce back to logistic regression and try to optimize that as far as possible because it's so much more interpretable? Something to consider. Um, EHR integration to extract 57 features in real time requires pipelines across modules. Flagging 40% risks alert fatigue. So, if we keep flagging everybody, then how long are they going to care that patients are being flagged and how often are they going to be doing something about it? They might resist those algorithmic recommendations. So, the trust must be earned with the physicians. Hospitals need transitional care resources, so coordinators, home visitors, costing, $500 to $1,000 a patient. Uh, the model is validated scientifically, but successful deployment requires organizational infrastructure, clinical buy-in, probably most importantly, as well as financial commitment. What we've accomplished. So 5 key findings emerge. First, model performance is strong with 0.683 AUC, which shows excellent generalization, only 1.3% points below validation. Catch 7 out of 10 readmissions with 50% enrichment over the baseline risk. Second, clinical efficiency is exceptional, screening just 13 patients per 1 readmission, so it's 50% more efficient than random selection, rivaling some of the best preventative interventions in medicine. Uh, Third, business value is substantial across hospital sizes with, 200 to 300% ROI on multi-million-dollar net benefits annually. Um, Fourth, fairness requires attention. A 17% point gap exceeds our 15% intervention threshold, demanding ongoing monitoring, as I said. And fifth, predictive features emphasize multidimensional clinical complexity over single diagnosis, validating our feature engineering approach. Lastly, so we've developed a validated machine learning modeling predicting 30-day ICU readmissions with clinically useful accuracy. This model is ready for the next phase, prospective validation, but not for production deployment yet. 3 critical success factors will determine real-world impact. First, we must validate these findings on live data from other hospitals to confirm our performance holds. Second, we need seamless integration into a clinical workflow. It can't disrupt the care, right? It can only help it. Uh, and third, fairness monitoring is non-negotiable. We identified performance variation across racial groups, and we'll continue tracking that. Broader implications matter here. We've demonstrated EHR's data predictive power for proactive care, validated a rigorous temporal validation methodology, and elevated fairness from afterthought to a core metric. Perfect being is the enemy of good. 0.683 AUC isn't perfect, but it's clinically useful and economically viable. Every readmission prevented spares a patient suffering and a hospital financial penalty. The model works on historical data. Prospective validation will determine if it works when it matters most in real-time clinical care. Thank you.